Welcome everyone, I am Sabbir Bhuya, Analog and Mixed Signal IC designer and founder of Analog Brain. In this first lecture, we are going to do something a little different. Instead of jumping straight into circuit topologies, we will go back to first principles and develop a mathematical model of an amplifier using what I call the BMR, the bare minimum requirement. By the end of this lecture, you will know exactly why an amplifier must be nonlinear at its core and why that's not a contradiction. It's actually the key insight that unlocks everything else. Let's get started. Before we define what an amplifier is, let's answer a simpler question. Why do we even care about amplifiers? Look at this list. The point is, amplifiers are not just one block in one system, they show up everywhere in analog design. Okay, we can see amplifier in PMIC device, data converters, RF and wireless device, and also in wireline, RX front end. Also in we can see amplifier in analog signal processing, sensor interface, and also in memory circuit. And rounding out the picture, clocking NPLLs, IO drivers, bias and reference infrastructure, startup circuits, reference buffers, voltage and current reference all use amplifiers in feedback. Okay, so the bottom line, as written right here, amplifiers appear almost everywhere wherever we need to detect, control or drive a signal. So if you want to be a complete analog designer, you need to understand this block deeply, not just how to use it, but how to model it from scratch. So now, what is an amplifier? The intuitive answer is an amplifier is a system that amplifies the input signal. Uh, now, this is the input signal and this is the output signal. The output signal is an amplified version of the input. Now let me ask you a direct question. Is V out greater than V in? Is the bare minimum requirement to call out something an amplifier? The straight answer is no. And I want you to really sit with that because this is where the most textbooks start and it's the wrong starting point. Why? Because voltage amplification alone tells us nothing about power, and ultimately the job of an amplifier is not to scale a number, it's to deliver more power to a load than was extracted from the source. Okay. So this brings us to a more precise question. When building an amplifier from first principles, what should be our starting point? Voltage amplification or something more fundamental? We want voltage amplification. Sure, I agree with you. Okay, but that does not mean it's the first item on our design checklist. Think about a step up transformer. Okay, think about a step up transformer. V out is greater than V in. Can we call it a voltage amplifier? Most people would say yes, but can it deliver more power to the load than the source provides? No, it's just a passive device. The power is just redistributed. P out and P in are almost equal or less than. P out is less than P in. So what about a step down transformer? Where I out is greater than I in, current amplifier, same argument applies. Now, here's the next question. Is it possible to amplify a signal with a one port network? Okay. The answer is no, and let me show you exactly why. A port is defined as a terminal pair where current enters one terminal and exits the other. So now the number of ports equals number of terminal minus 1. With only one port, your input and output share the same terminal. There is no separation. Okay. Uh, so so why can't one port network amplify a signal? Two fundamental reasons. First, the input and output ports are not separate. There is no independent output, right? Second, to get amplification from one port, you would need a negative port resistance inside the black box or a negative source resistance on the signal side. And fundamentally, in standard CMOS technology, we don't have devices with negative slope in the IV characteristics at DC. But in discrete world, you have tunnel diode, but that's a very specific case and not what we are working with here. So the conclusion is clear. A one port can not amplify. We need at least a two port. Let's see some mathematics. Okay, so this is our voltage source, this is the source resistance. I model the black box as a resistance which is one port. Okay, now I have applied some voltage divider rule. V out by Vs, R black box, Rs by R black box. So for make V out is greater than Vs, modulus of V out by Vs will be greater than 1. Now R black box by Rs plus R black box will be greater than 1. So Rs is less than 0 of its or if rs is fixed, then our black box is less than 0. Or you can you can get it with some numbers. Okay, our black box is equal to negative 9 ohm and rs is equal to 10 ohm. So v out by vs is equal to 9, which is greater than 1. So we get here amplification, but this our black box is negative 9 ohm. So we can't do it with a single port, right? We can do it with a single port. So now uh, going forward going forward so we have established that we need a two port network to model our amplifier. Okay, uh, at least for giving an additional power source. So now V out equals A times V in. That's our final target. That's what we want our amplifier to do eventually. But we cannot use that as our definition because it does not tells us anything about where the energy comes from or how the system behaves physically. So the real question becomes what quantity should amplify as our BMR. Okay. Uh, to answer this, let me refer to a classic reference, Cedar Smith, microelectronic circuits. So we have to analyze the four amplifier types. There are voltage amplifier, current amplifier, transconductance amplifier, and transresistance amplifier. So for voltage amplifier, the input is voltage and output is also voltage. So we have voltage gain, current amplifier, input is current, output is also current. So most of the designer are start with voltage amplifier and V out is equal to A times V in, and they called it amplifier. So this is not the universal amplifier. We want to design a block. We want to model a block such that they satisfy all the four amplifier types, right? So one is voltage, one is current, another is transconductance amplifier, means your input is voltage but your output is current. Another is transresistance amplifier where input is current, another is voltage. You can I can tell you something that this transconductance is amplifier is nothing but a common source amplifier. So you can common source, common gate, common drain, all these three. But so that's the thing. So we want to make a model that can that will universal. Okay, a universal model. We need a universal model. So we have a intuition that only voltage amplification is not enough. We want something more. So we want power amplification, and that only quantity will valid and hold all the four amplifier types. Okay, going forward. So here is our definition, clean and precise. An amplifier is a two-port LTI system that can amplify the power of the input signal at the output port without distorting it. When I say it's LTI system, linear system, I already mentioning without distorting it. Okay, LTI means without distorting it. So if I exclusively not mention the without distorting it, it's also define the actual definition. Okay, the signal source will connect at the input port. Okay, the load will connect at the output port. And now the problem statement, which is what we will design to. We want to design a block such that the power delivered to the load is greater than the power extracted from the source. So this is the BMR, the bare minimum requirement, power gain, not voltage gain, not current gain. Okay, power gain. So this framing is important because it immediately raises the next question, which is where things get really interesting. Okay, let's see. So the linearity and non-linearity paradox. Now we invoke the law of conservation of energy, because one can say how you can your output power greater than the input power, P out is greater than P in. Yeah, you are validating the law of conservation of energy, you are validating physics. Okay, we invoke the law of conservation of energy. Energy cannot be created or destroyed, it can only be transformed or transferred between systems. So if we want the output power to exceed the input signal power, we cannot violate physics. We need an additional energy source. Okay, and that source is VDD, the DC supply. So congratulations, we are not violating any first principle. We just need an external DC source. But now comes the critical question: how do we transfer this VDD power, which is a DC source, zero frequency, to our signal, which sits at frequency of omega? Okay. So can we simply use an LTI system to do this? Okay, the straight cut answer is no. And this is the paradox at the heart of this lecture. Let me prove it to rigorously, starting with LTI, what LTI actually means. And where is the paradox? We want linear time invariant system, we want linear system, but a linear system cannot transfer power. So okay, so what to do next? Okay, let's see. Let's see. Let's break LTI into its two parts, linear and time invariant, and examine each one. A linear system, okay, so a linear system satisfies superposition, which has two components. The first is the law of additivity, LOA, and the second is law of homogeneity. If law and additivity and law of homogeneity both holds, then the linear system, it is called linear system, and it holds the superposition. Let's see. Let's see. It is a system, okay, and I give a input to this system x1t. I have an output y1t. Okay, so I have the same system. It is the same system, but I tried with a different input x2t, and I have an output y2t. Now I will add those two output with a summer, and I got y1t plus y2t. Now I will do different thing. I will add the input first, then I will take the output from the same system. Okay, from x1t and x2t, I add a summer, and I got x3t, which is x1t plus x2t, and I give this to my system, the same system, and I got a output y3t. Now if law of additivity hold, if only if y3t is equal to y1t plus y2t. Okay, so these are shown in the block diagrams on this slide. Let me now show you what this look like with a real design, with some Python simulation. Okay, let's see. So this is the lower verification from our Python simulation. We have two signals, a 1 Hz sine and a 3 Hz sine, pass through an RC low pass filter. Path A process them separately. Okay, path A process them separately, and path B add them first, then process one. The overlay at the bottom shows the two curves sitting exactly one on top each another. So this is input signal x1t, x2t. This is x1 1 Hz, x2 3 Hz. Okay, through the system separately, and this is combined input through the system. Okay, so this is path A and this is path B. We see the both are the results are almost same, and we overlay, right, we overlay path A and path B together, and see there is not much difference. This is the verification of law of additivity, so we can say law of additivity verified. Okay, so if both LON and LOH are satisfied, the system holds superposition. And superposition is just not just a mathematical convenience; it is the foundation that allows us, right, that allows us to apply KCL, KVL, Thevenin, Norton, and every other circuit theorem we use in linear circuit analysis. If the system is not linear, none of those tools are valid. Keep that in mind. We'll come back to it. So we'll now see the law of homogeneity. This is our system, and I applied input x of t, and I got y of t. Now I scaled my output with a scalar k, and my output is ky of t. Okay. Now in a different path, path B, we will input the we'll scale the input first. Okay, so this is k times x of t, and it is going through the system, and we have y prime t. So these two outputs will almost similar, will have similar, and will have equal if only if law of homogeneity hold. So law of homogeneity will hold if y prime t is equal to k y of t. Okay, so and here is the LOH verification. Three scaling factors: alpha equals 0.5, 1.0, 2.0. Path A, scale the input, then process. Path B, process, then scale the output, and all three overlay are perfect. Okay, so the LOH also verified. If you need the Python code, please comment, and I will give all the Python source code. Okay. So for now, and here is the full superposition verification, combining law of additivity and law of homogeneity in a single figure. Two section, LON top, LOH on the bottom. Okay, and here is the combined form. So here we got some first order Butterworth low pass as our system. Okay, here is the cutoff frequency where 2 Hz. Okay, let's see. So the superposition is verified. Now we'll do some work in time invariance. Okay, so what is time invariant? Time invariant means the system itself doesn't change with time. Okay, the system itself doesn't change with time. If x of t gives y of t, then x of t minus t naught, a delayed input, gives y of t minus t naught. What I mean, the same delay in the input, the same does not the system does not care when you apply the input. Its behavior is fixed. For an amplifier, this is exactly what we want. We want active amplification, not frequency shifting, not dependent behavior. Now there are cases where we intentionally use a time variant system. Okay, time variant system. The mixer is the classic example. The mixer multiplies the signal by a local oscillator which is explicitly time varying. That's how it shifts frequency, but that's a different topic. For our amplifier model, we want time invariance. Okay, we want time invariance. So now like this is a system, and I take a input x of t, and I got a output y of t, which is delay by t naught. Now my output is y t minus t naught. So now for different path, I add delay to my input first, then I the delayed input is passing through the system, and I got some output y prime t. So if the system is time invariant, means the system itself doesn't change with time, the system is time invariant. And only if this y prime t and this y t minus t naught is equal. Okay. So here is the TI verification from my Python code. So 3 time shifts I use 0.3 seconds, 0.6 and 1.0 seconds. Okay. Path A shift the input, then process with the correct filter initial condition. Path B process, then shift the output, and all three overlays are exact. So let me break it down. Reference input is x of t, reference output is y of t, h of x of t. Now I shifted the input t minus t naught, so 0.3 second. So here is the here was the peak. Okay, so it shifted 0.3 second. Okay, let's see, it shifted 0.3 seconds. So this was the original signal, and this is the shifted signal. So this peak is shifted here. Okay, and this is the ultimate result. So this is path A, and this is path B, and this is the ultimate overlay. Okay, so we can say our TI verified. Okay, now hence here is the full LTI verification, law of additivity, law of homogeneity, and time invariance all in one figure. Section, three proofs, and every check passes at machine precision. So we have a fully verified LTI system. Now what happens when we plug VDD into it? Okay, let's see the Python output for this exact scenario. So before that, I'm going to show you why a linear system cannot do active power amplification even when there is an additional DC power source available. Okay, simply I'm saying that linear system cannot transfer power from a DC 0 to signal frequency in output. It just shift the output voltage up, no scaling the VNT. Okay, let's be clear our input signal is vnt bp sine omega t plus theta. For simplicity, you can consider theta is equal to 0, no epoch, no initial lead or lag. Okay, we want v out t is equal to some constant time vp, k, some scalar. Okay, k times vp sine omega t plus theta, but we don't want any type of DC shift. Okay, we want pure peak scaling, no time shifting. It indicates the final product amplifier should behave like an LTI system for faithful amplification. But when we took an LTI system for modeling the black box, we found out that it just upshift the input signal, and we got V out BP sine omega t plus theta plus that constant, which is undesirable, and we are now stuck in a linearity and non-linearity paradox. Let's see the output of the Python code for this matter. Okay, and here is the visual proof. Look at the input spectrum, a clean single tone at the signal frequency. Okay, okay, and this is VDD 3.3 volt, this is 1 volt. So this is system model superposition, two port LTI system. Okay, now we can see the output y of t, where the signal peak is in 4 is started from this 3.3. Okay, and this is 1, so this is 4.3. So and we decompose the output AC and DC part, and we can see this and we can realize this is not the amplification. The output is just shifted up. Okay, and if we see the input spectrum at 100 hertz, this is the input spectrum, which is 1 volt, and this is the output spectrum. DC is in 6.6 volt VDD and energy, but this is also in unchanged 100 hertz, which is unchanged. Okay, and this is in 1 volt, and you can see it in your power consumption comparison. Your input AC power and your output AC power is almost same. So the paradox is proved. Okay, the paradox is proved. Okay, now going forward, so we can't use a linear system. Okay, we can't use a linear system. We have one option left, a non-linear system. And importantly, we are not abandoning time invariance. Okay, the paradox was specifically about linearity. Time invariance cost us no problem. Okay, so we keep that property. Now I will take a nonlinear system and do some mathematical manipulation to check whether it can actually do what we need. The most basic nonlinear mathematical function is a polynomial. So let's start there. We'll model our system as a polynomial, specifically a multivariable polynomial, because our output is a function of both b in and bdd. B out is a function of b in and bd. Is a multivariable function. That's why I need a multivariable polynomial. So p of xy, a1x plus b1y to the power 1 plus a2x plus b2y to the power 2 plus dot dot dot, and uh, this is not beautiful. uh, uh, this is a beautiful expression. P of xy is equal to summation of I is equal to 1 to the power infinity aix plus biy to the power y. This is more beautiful. Okay, I like beautiful equation. Okay, now this is a black box two-port nonlinear device. This is my VDAD, this is my VSS, and VSS is this negative port is connected to VSS. Okay, V in T, RS, this is RL. Okay, so we took multivariable polynomial for modeling because here V out T function V in VDD, which is a MBF multivariable function. So now here is the multivariable polynomial model. We explain V out as a power series in V in with coefficient that depend on VDD, especially on the DC operating point set by VDD. This is mathematical framework. The key insight is that the coefficients of these polynomials are determined by VDD and the operating point. VDD enters the picture through these coefficients. It does not add to the output directly. Okay, it modulates how the system responds to V in. Okay. Uh, so this is V out T, A1 V in plus B1 VDD plus A2 V in plus B2 VDD square dot 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 continues. Okay, V out T. So I applied A plus B whole square formula, A square plus 2AB plus B square here. Okay, then I take V in common out. A1 plus 2A2 V2 VDD V in plus A2 square V in square. It continues. Then now let's plug in V in of t equals a times cosine of omega t, a pure sinusoid, and expand the polynomial. Okay. Okay, I expand the polynomial and I do some mathematical manipulation here. I multiply with half and 2, and this is the famous trigonometry formula, right? 2 sine square a. 2 sine square is equal to 1 minus 2 cos a. Okay, so 2 sine square omega t is equal to 1 minus cos 2 omega t. Oh, there is the harmonics. Okay, there is the harmonics. So what comes? Look at what comes out. The DC bias term is a constant, or here is the thing. Here is the amplification factor. So now it is proved that a nonlinear system can transfer power from BDT to V in T. Okay, some constant is multiplied with Bp. Okay, a1 plus 2 a2 v2 vdd is multiplied with Vp. Okay, Bp sin omega t plus half a2 Bp square, and we got some harmonics cos 2 omega t. Okay, so the harmonic terms 2 omega, 3 omega, and so on, these are the trade-offs. The nonlinearity that enables power transfer also generates frequency components that were not in the original signals. So this is not a choice, it's a mathematical consequence. Every nonlinear systems driven by a sinusoid will produce harmonics. Okay. So the polynomial expansion of sine squared gives cosine 2 omega, sine cubed gives sine 3 omega, and so on. Okay. So let's state what we have proved mathematically. Uh, a nonlinear system can transfer DC power to frequency omega. Okay, proved from first principle of mathematics. The consequences are the amplitude of the signal at the output is increased. Okay, that's our amplification. Additional frequency components appear at harmonics of omega. But here's the second trade-off, and this one is more fundamental than the harmonics. Because the system is nonlinear, we can no longer use KCL, KVL, Thevenin, Norton, or any standard circuit analysis theorem. Those tools requires linearity. We just proved our system must be nonlinear. That's another paradox, and this is exactly where lecture 2 will begin. Now let me show you some Python visualization of this. Okay, and before this, we are telling that we will intentionally inject some THD to see the effect of additional frequency component, and also a proven point can be visualized from it that nonlinear system can transfer power from VDD frequency 0 Hz to VINT some 1000 Hz efficiently. Let's see the output of the Python code for this matter. So here is the output, and my input signal VINT. Okay, so it shows that a nonlinear system can transfer energy to signal frequency omega but introduce harmonics. Okay, so the output is now amplified. So here is also harmonics, amplified plus harmonics. Okay, so AC comparison, the power gain is 10x, and we can see here the input it is 1000 hertz. Okay, the amplitude is 0.3, here 0.3, input 1000 hertz, output spectrum 1000 hertz. Okay, and it is not now 0.3. Okay, it increased in 1f we see it's 0.9272. So the power gain is 10.1 times, but the trade-off here is the 2f, 3f, 4f, and 5f. So there is a thing. So the key results shown here: the output DC power is greater than input DC power, the true amplification, VDD DC power is consumed, harmonics at 2f, 3f, 4f appear in output spectrum, and THD, total harmonic distortion, quantified. Okay, okay, so let me summarize what we covered. We started with the importance of amplifiers. Okay, basically we start with the importance of learning amplifier in depth, then we try to define amplifier with our common sense and find out the problem in the definition. Then we start to find the template for our model, starting by a one port network, and see why it's fundamentally not possible in analog IC. Then we focus on the quantity which should be amplified and define our problem statement and amplifier definition. Now we know what is an amplifier, two-port LTI system which can deliver more power to load than it extracted by the source. Then we conclude that it is not possible to break the fundamental law of physics, P out is greater than P in, without an additional source. So we conclude that we need an additional power source to transfer power in V in of t. Okay. So then we entered into an linear nonlinear paradox where we don't have the ability to transfer VDD power to signal power with linear system, but we want linear system. To understand this critical paradox, we go deep into the LTI system from the signal and system perspective and prove that it is the fundamental property of linear system to not transfer power in different frequency. Okay, DC to signal frequency. So we proved rigorously. Okay, we proved rigorously using LOA, low and Python simulation that a linear system cannot transfer power from DC to signal frequency omega. By superposition, VDD energy stays at zero. Okay, zero frequency regardless of the circuit. We then took a nonlinear system, model it as a multivariable polynomial, and mathematically proved that a nonlinear system can transfer DC energy to a frequency omega. But we immediately found two trade-offs. First, harmonics at multiple omega are introduced. Second, more fundamentally, with a nonlinear system, we lose the ability to use KCL, KVL, and all circuit theorems. We are now stuck at this exact point. Okay, uh, and the solution to this second trade-off is the subject of lecture 2. So what is coming in lecture 2? We start exactly where we got stuck. The KCL KVL problem, we already know we want power amplification and we want a linear system for circuit analysis. These two requirements seem contradictory. In lecture 2, we'll develop a framework to linearize a nonlinear system using the Taylor series, the magical tools of mathematics. From that analysis, we'll see the natural origin of small signal analysis and how the small signal model emerges from first principles. Okay, then we'll use our two-port linearizing framework, apply the admittance matrix to model our amplifier, replace the model with a controlled current source, and finally realize we it with a MOSFET. So that is the complete journey from first principles to the small signal model. Okay, don't miss it. So now the references. This slides contains the full reference list, YouTube course and textbooks for the entire course. A few highlights for signal and system. OpenAIM MIT lectures are the gold standard. For analog circuits, Nagendra Krishnapura, Shanti Pavan, Behzad Rajabi, YouTube are excellent. For books, Cedar Smith for fundamentals, okay, and Rajabi Simos analog circuit design for advanced topics. And Alan Holberg is a solid reference. Okay, so this is the YouTube reference, YouTube reference to, and this is the book reference with control system, with signal and system. Okay, so the thing is, what I want to tell that all the reference are given only for gathering knowledge. Okay, same knowledge appear in most of the places. Be choosy. Okay, be choosy, pick what you need, but master at least one. For reference, master at least one book with all exercise and practice in simulator. Without action, knowledge is nothing. Okay,